Good afternoon. First of all, thank you very much to the organizers of the conference for inviting me over to give this talk and the workshop yesterday. Now that it's quite a bit further than it used to be when I was living in Sydney, so it's very nice to be here. What I want to do today is talk about our work at IHK on scripting blockchains. So let me ask, who has any experience in programmatically interacting with a blockchain, Bitcoin, Ethereum, whatever? Okay, so let me give you a bit of background. So the idea is we have this ledger thing in the middle, and people have funds, cryptocurrency, in this case ADA, that's the cryptocurrency of the Cardano blockchain. And these people have wallets from which they issue transactions. And these transactions are recorded on this ledger. But they don't overwrite anything because this data structure is immutable. Hello, functional programming. So, but it's a bit boring to just have money on this thing, right? So maybe we can have some other information as well, maybe what we are using those funds for. Or maybe even more general information. Maybe we want to track some real-world resources and properties of them. For example, we could imagine somebody, in this case Alice, is selling some timber to Bob, and Bob sells it on to Charlie in the form of a door frame of which he claims certain properties where that timber came from. Now, if we want to do this on a ledger and we want to be sure that the parties actually follow the constraints they're claiming they're constraining, we need something which we call validation. We need to check that this information is consistent by whatever rules we impose. Now that means that when we construct this immutable data structure, we have to check for every transaction, it's okay to put that transaction in there. We have to do that during the construction. But there's other computation too. I mean, outside of the ledger, which you can regard as a glorified database, we also have to do processing, we have to get events, we have to submit transactions to the ledger, and so on. So really, we are doing computation on two places. We really need a proper programming language at this point. And we need it to be able to specify computations on both the chain itself during validation and with the clients in those cryptographic wallets. Now, these computations on the server, well, there's actually not just one server, there are many servers. That's the whole point about a distributed consensus ledger. It's many servers collaborate in constructing this immutable data structure. So how do we know nobody's cheating? Well, that's where the cryptography comes in. And there are basically two ways, major ways, in which proof that all the parties constructing the chain do the right thing is constructed these days. So on one hand, we have what Bitcoin and Ethereum is using. And I'm sure you've read all the headlines about how much energy this is using and that it's ecologically quite questionable approach. And then there's a second method, which is called proof of stake, where we use the party's investment in the system instead of this proof of work, where really we are wasting energy to solve cryptographic puzzles, just for the sake of showing that we've invested this energy. So this is basically the setting in which our work is established. And this is in the, on top of the Cardano blockchain. So what's Cardano? Cardano is a proof-of-stake system, so we don't want to waste any money. In fact, a Cardano node has been shown to run on a Rock Pi that's a little bit bigger than a Raspberry Pi, so you don't need a lot of energy to run it. And there are all kinds of interesting properties to that blockchain, which I don't want to discuss any further. What I'm interested in here is the functional programming aspect, and especially the scripting on top of the chain. Now, This work is, has been done by the Plutus team. I don't want to get all the credit here. It's quite a few people involved, including Phil Wadler, who will give the keynote tomorrow. And the system which we're working on is called Plutus, and there are 3 ways in which it is fundamentally different to other systems which a few people here have experience with. So on one hand, we use functional programming to gain safety and security properties and actually use formal methods to prove something about them. And I will say very little about this because I don't think I have to convince anybody here about the merits of functional programming. But then what I want to really talk about is the ledger architecture, how this is really supporting functional programming, and how we are doing this on and off-chain programming in one framework. All right, so the little bit I want to say about functional programming is we have to represent those on-chain computations somehow on the ledger because they're executed during validation. So all the servers which contribute blocks to the blockchain need to have access to this code. Typically, Bitcoin is using something called Bitcoin script. Ethereum is using something called the Ethereum virtual machine and its instruction sets. So people are really set in this space on stack-based machines with bytecodes and stuff, which is quite complicated. So what we are doing, we are using a typed calculus. In fact, we're using a typed lambda calculus as our intermediate language. Why is that useful? Well, first of all, we don't have to build a complicated virtual machine. We can do with an abstract implementation of an abstract machine derived from the semantics of this calculus. And secondly, we use system F omega, which is a well-studied system. There are papers, books about the semantic properties. So we actually know a lot about this language, much more than we know, say, about Ethereum virtual machine instruction codes. And this core language, its semantics, that's the entire, it's a CEK machine. That's the rules for the operational semantics. And our Haskell implementation is quite faithful to these individual rules. So if you look at this LaTeX presentation and you look at the Haskell code, it's quite easy to see that the two are in correspondence. But we didn't stop there. And I think Phil is going to say some more about this tomorrow. We have a formalization of the meta theory of Plutus core in Acta. And we are working on using our integrated test infrastructure to automatically test the Haskell implementation against extracted interpreter from the Acta formalization, so that we can be even more confident about those semantics coinciding. So where do we use this Plutus core? That's the point where we have to look at the ledger. So I presented the ledgers as this conventional append-only data structure where, well, what are you interested in? You're interested in the funds for every single person. So this is a little bit like a setting in a bank with bank accounts. We call this the account-style ledger model. Now, there's actually an alternative, and this is how Bitcoin represents its information as well. So that's where the structure originates from. And it's a bit more akin to how you handle banknotes. So imagine these 3 people, Alice, Bob, and Charlie, they actually have these funds in their hand. And then Alice does a transaction and pays something to Bob. Then she needs change. So we need to split this 100 ADA into what I'm going to pay and what I'm going to get back and am going to keep, or Alice is going to keep. And then when Bob wants to pay, he takes the funds he took from Alice, combines them with what he already has, and then again, there's some leftover change, and the rest is going to be paid to Charlie. So now in this model, it's less clear who owns what. In fact, ownership is defined by the ability to spend those nodes which haven't been used yet. Now, this is why this structure is called an unspent transaction output ledger, where cryptographic proof that you can spend funds which haven't been spent in the data structure yet defines ownership, basically. Now, this structure is nice because, well, it's actually a data flow graph. It's an inherently functional structure. All data dependencies are fully explicit, whereas in the account-based model, well, you may remember your introduction to object-oriented programming, or we have accounts, we send messages between accounts. It's an inherently object-oriented imperative model. Now, we are talking about concurrent distributed data structure. Should you use something based on an object-oriented mutable state is everywhere model? Is that a good plan? I don't think so. I rather have the functional model which has this explicit data flow structure. So this is the data structure underlying the Cardano ledger. But now if you look at the two main most popular blockchains today, then there's Bitcoin, which has this UTXO model, as I said. And then there's Ethereum, which uses this account-based model. Why? Well, because the scripting functionality of Bitcoin is really very limited. And Ethereum, the whole point about Ethereum was exploring how we can have maximal programmability on top of a blockchain. And in fact, the Ethereum language Solidity is so expressive, you can write all this buggy code with which you can lose millions of dollars. Isn't that great? So can't we maybe have the best of both worlds? Can we have this functional data structure, but with an expressive contract language? So let me tell you a little bit something about how this validation works. So if you have a transaction and you want to spend an unspent output in black with another input to another transaction in red, then there's some scripts involved. So the output, the black edge, has the value which is being spent and a script, in our case in Plutus core, which checks that they're spent in a way which is agreeable to whoever put this transaction on the chain. And the spending transaction has to provide another script, the redeemer in Bitcoin, it's called the witness, which then we apply the validator to the redeemer, because the validator is just a predicate, and run this code. And if the result is true, well, then the connection is allowed. Otherwise, the second transaction, the one on the right-hand side, is rejected, thrown away. Now, this model is very limited because the validator has no information whatsoever about any environment except what's in the redeemer. So let's extend this model a little bit. Let's give the validator a little bit more information. So in addition to the actual validator computation, we provide it with some user-defined data. For example, state of a contract that is currently being processed. And also, let's supply it with all the information about the current transaction. Then validation gets slightly more complicated. We apply the validator to the redeemer, as before, to the value, the data, this extra data, and the transaction information. Now this we call the extended UTXO model, and it leads to vastly more expressive scripting capabilities, but it still retains the same functional data flow structure as the original UTXO model. In fact, and that's very crucial, computations, evaluation of validator to redeemer applications, they're purely functional, pure in the sense of no side effects. So as a result, as a side effect of that, this computation which we have to execute to check that we can make a connection between two transactions is a pure expression. Which means if I execute this thing and I use the same transaction and the same value, then I will always get the same result. But it will also always take exactly the same resources. So if I want to know how much resources do this computation take on the chain, I just run it off-chain first, count the execution count of the abstract machine, and I know exactly what the execution fees are. Now, if you ever used Solidity on Ethereum, then you may have come across stack exchange questions like this. Oh, I tried to run my smart contract, and I didn't give it enough fees, and now all the money is lost, and I have to rerun it again, and I still don't know what the fees are going to be. So in our system, this is impossible, because everything is perfectly deterministic. So this is one of the payoffs of just sticking to your purely functional model and not using any of this side-effecting nonsense. All right. So much for the ledger. So what's this full stack business about? Now, if you want to write a smart contract application, decentralized application on something like Solidity, what's the kind of code you're going to write? Well, let's take a simple example. Let's say we do a simple crowdfunding setup. So there we have a crowdfunding campaign. There's a deadline by which everybody paying into this campaign has to pay enough in that a particular funding goal is reached. Now, if this funding goal is reached, then the campaign owner can take out all the funds. If the funding goal is not reached within the deadline, then everybody gets their stuff refunded. And in case the campaign owner runs away, then, of course, we also want participants to get a refund. Now, if you do this on Ethereum, you're going to write this Solidity, random programming language with some random people invented. And then you may think you're done. Now, you have to write all this JavaScript code as well. And actually, you have to write more JavaScript code usually than Solidity. And then you can argue about which is the worst programming language, but I leave that to you. Overall, you are ending up with this kind of two-level thing for off-chain computation in JavaScript, which run in a user's wallet, on-chain computation Solidity, which run on the blockchain. And, well, we are programming language people. We call this a staged programming model. It's a two-level programming model. It's not presented as that usually, but that's what it is, in fact. Now, if you do this with JavaScript and Solidity, it's quite inconvenient, because sometimes you have to move code from one to the other. Well, then you have to rewrite it in another programming language. That's no fun. It's also quite complex. At the minimum, you have to learn 2 languages. And it's fragile, because there's no check of APIs between the two. The two actually communicate via adjacent protocol in a network connection. So it's quite ad hoc. Now, so what we are proposing is, hey, use Haskell for the off-chain code. And by the way, also use Haskell for the on-chain code. So now we've only got one programming language, and we use a meta-programming facility of Haskell to tie the two together. And then we have an integrated system, one programming language. You can copy code from one world to another, no problem. It's compact. And actually, we get type checking across the whole system, because it's one program in one programming language. So how does this look like? So let's take this crowdfunding example, the function where you contribute something to the campaign. So you have a campaign description. You have a certain amount value that you want to contribute. Then, well, first of all, we check you contribute something positive. And then all these transactions, they're submitted from a wallet, because whenever you submit transactions to a public blockchain, you pay some transaction fees. So there's always necessarily some cryptocurrency involved. So we get the key of the person paying in, because in case we get a refund, we need to know where that has to go. And then we create a transaction locked by a script. So we describe the validator here, basically. And how we are describing the validator code, we'll see in a moment in this contribution script function. And then we state the value that we're going to pay in, and we put our public key in as the data script of the additional data information which I introduced in the extended UTXO model, so that the validator script knows who is allowed to get a refund, basically, of this particular value. And then we register basically a callback. We call it a trigger that is triggered in case, for example, a refund is due, so that the contract code can automatically submit a transaction to get the refund. All right, so this is our off-chain code. How about the on-chain code, the validation code? Well, it's still Haskell, but we are going to use some template Haskell magic. So that's the blue background, basically. So we have template Haskell quotations. And we define a lambda function, which again gets the campaign information as one of its arguments. An action, whether we are collecting the funds from the campaign or getting a refund. And the transaction information. And then it just pattern matches on the transaction in order to extract some information. And does a case distinction over which of the two actions we are currently in for. If there's a refund, if it's a refund action, well, this is only permissible after the collection deadline. So in case the campaign hasn't been funded or the owner didn't collect the funds. And we check the outputs, secondary. And then we check that the signature on the transaction is actually from the person who put those funds in. So the refund is going to the person who put in the funds in the first place. And that uses as information the public key which we submitted together in the with the original transaction. Now, in the second case, if the campaign owner thinks the campaign was successful and they want to collect all the paid-in funds, then, well, we have to be after the campaign deadline, but before the collection deadline, before people can claim refunds. And we need to check that the total amount of paid-in value is bigger than what the campaign target, the funding target was. And then, of course, the transaction has to be signed by actually the person who is really the campaign owner. So these are basically how the validators, you see how the validators, they're really predicates. They check the conditions of whatever particular case in the state space of the contract we are currently looking at. And that's it. So it's all just simple Haskell code. So I hope you got a little bit of an idea of how these scripts look like. And they're really just quite simple Haskell programs. Now, to look at the big picture, so if we have source code like this, how is the execution? How does this work? So as I said before, we have to look at on-chain computations. So that's what happens during transaction validation on the chain, and off-chain code, which happens in the wallets of users. Now, when we compile Plutus contract, then we are generating some off-chain code, which one way or another gets into user wallet. And it actually encapsulates Plutus core for all the possible on-chain computations it might want to submit as part of a transaction. And then, let's say, a user clicks on the button for the contribute action in their wallet. Then we submit a transaction which is logged by some of the Plutus core embedded in this particular off-chain code. And this is then validated by the chain. If it's accepted by the chain, and we didn't cheat, the transaction is integrated. And wallets generally monitor blockchains for events on the chain. So usually this is confirmation of blocks. And then these events which come from the blockchain into the wallet, this is what typically leads to these triggers where the off-chain contract code gets an event back to which it then can react. For example, maybe this transaction was the last one needed for this campaign to be successful, and then a trigger in the wallet of the campaign owner would submit a transaction to collect the funds. So this is the overall architecture. Now, so Plutus overall is basically Haskell scripting for the Cardano blockchain. And if you want to give it a try, we have what we call Plutus Playgrounds. It's an online web system where you can write this code, and we also have some example contracts for you if you want to get started. And this is all executed on a functional simulator of the blockchain, where you then get information about what happened, who got what, and so on, the UTXO graph. All the code is, of course, open source. It's in the Plutus repository of IOSK. And if you want to know more, in December, we had an event in Edinburgh with quite a few talks, and they're all online as well. So thank you very much for your attention.